Hello, Honors Chemistry, and welcome to your Chapter 14 review. I don't know how many videos this is going to be, but we're just gonna go and see what happens. All right, so obviously there's a whole lot of qualitative stuff, so make sure you go review that. It's literally from your book, or from your outline, or from your class notes, right? All those places will have excellent things for you to look at. In addition, the titration lab is a great thing for you to consider as you're reviewing. All right, equations you need to know, right? You need to know that the hydronium ion concentration times the hydroxide ion concentration for an aqueous solution at 25 degrees Celsius is always going to be equal 1 times 10 to the negative 14th, right? And from this relationship, right, we understand that hydronium and hydroxide are inversely proportional, right? As the concentration of hydroxide goes up, as this goes up, this must go down because they're tied together by this one value for all things in aqueous solutions at 25 degrees Celsius. From here, we can also derive our pH equations, right? So for example, pH is equal to the negative log of my hydronium ion concentration in molarity, not moles, so make sure you're thoughtful when you do your work, right? pOH is equal to the negative log of my hydroxide ion concentration, right? And then it turns out that pH plus pOH is equal to 14 because of this relationship, right? As in the negative log of this would be 7 and this would be 7, so the sum would be 14. Yes? All right. Moving along. So those are all equations that you need to know. There are also the reactions that you need to know, like types of reactions, so make sure you go back and look at that. Same thing with like limiting reactant math, which a lot of you guys seem to have forgotten. What else? Yeah, mostly that. All right, let's go ahead and do some math. All right, or practice problems, I guess would be better stated. All right, aqueous sulfuric acid is reacted with solid lithium oxide. So we're actually going to do number 15 for this, right, where we're going to practice writing a net ionic, which means that, yes, we're going to start with a complete molecular. So sulfuric acid, H2SO4, aqueous, is reacted with solid lithium oxide to produce what? Right, double displacement, specifically neutralization, because this is a what? Right, an anhydrous base. So we would get Li2SO4 plus H2O, and we'd go back and look at our balancing, and yeah, we're good. Okay. Oh, and this would be aqueous because this is always soluble, and this would be a liquid. Now we need to dissociate this into their respective ions if they dissociate, right? Here we have sulfuric acid, which we did not go over memorizing strong acids and weak acids. But in this case, so if you were to write your acids dissociated, that would be okay, and I would accept that regardless of the acid. So here we have sulfuric acid, which means I get 2 H pluses plus a sulfate, plus I get what? Right, I get this because, ding, 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 it's a solid, right? It must meet 2 criteria to dissociate. It must be aqueous and ionic, these being an exception, strong acids being an exception. All right, yes, this is aqueous and ionic, so this is going to do this. And this also does not meet the criteria for being aqueous and ionic. We'll cross out what cancels on both sides. Everything else becomes my net ionic. So then we'd have 2H plus my solid lithium oxide gives me 2 lithium plus H2O liquid. Yes? Net ionics. All right, next up, let's do some calculating pH. So if I want to calculate the pH of this solution, I need to figure out, right, the H plus concentration in a solution of barium hydroxide. So first of all, this is super important to note, right? As in, if I have 1 molar barium hydroxide, I actually have, right, 2 molar hydroxide, yes? All right, so then if I have 2 molar hydroxide, I'll go ahead and take the negative log of 2, and that's going to give me my pOH. And so the negative log of 2 is equal to negative 0.3 And then my pH equals, well, pH plus pOH equals 14. So if I take this into account, I'm going to get 14.30 as my pH, yes? And then some of you might be like, well, isn't the scale 1 to 14? Not really, right? Because it just depends on our concentrations. That is the standard range, yes, unless we start to talk about concentrated acids or bases. Okay, next up we have this, where if we want to do pH, we need to know the H concentration. This is going to dissociate at a 1-to-1 ratio, which means that I have 1.2 times 10 to the negative third molar H plus. So we're just going to take the negative log of 1.2 times 10 to the negative third, and that's going to give me my pH, which is equal to whatever is in the answer key. All right, next up, a solution with, so here we're trying to find the, I think I asked you for the hydronium ion concentration. So a solution with a pH of 0.22. So basically we need to think about how to undo that. So if I know that pH is equal to the negative log of H3O plus, right, 10 to the negative pH is equal to my H3O plus. So then, if I have this, I know that if I take 10 to the negative 0.22, that's going to give me my H3O plus concentration, which I believe is this. As a follow-up, we have this. pOH is 4.44, and we have a couple of ways we can solve this, right? pH plus pOH equals 14, right? Which means that in this case my pH is going to be 14 minus that, right? So if we were to take 14 minus 4.44, that's going to give us our pH of, and then from here we can do 10 to the negative 9.56, right? Alternatively, we could, which will give us a number, obviously, 2.8 times 10 to the negative 10 molar, okay? Alternatively, we could undo this and get our OH minus concentration, right? And then get to my H plus concentration via KW, right? And then do this last step. Well, actually, I guess there wouldn't be a last step at that point, yeah? Does that make sense? So we could do that. We could go from here to here, 10 to the negative POH, that says POH, would give me my OH minus, right? And then from there I could use KW to get to there. Either way, same final answer. Yes? All right. Next up, what mass of sodium bicarbonate, mass is my question, is needed to completely neutralize 2.5 liters of monoprotic acid having a pH of 2.48? So, let's start by, this is a reaction, so let's write a reaction, right? I know I have HA, and I know that I'm going to react that with some sodium bicarbonate. And I know that that's going to give me a salt. And I know it's going to give me water. And it's going to give me CO2. And we would go back and balance, and indeed it is balanced, right? So I would like to know the grams of this, and I know I have 2.5 liters of this, which means I need to know the molarity of this. All I know is this, but, right, this is the concentration of that in a roundabout way, right? So 10 to the negative 2.48 is going to give us our concentration, right? So this is going to give us 0.0033 moles of H plus, right, per liter. And I know that all this H plus came in a 1-to-1 ratio from here, yes? All this H plus came from here, which then means that I have 0.0033 molar HBr. Yes? All right, so then we can do our next steps, which means 1 mole of HBr for every 1 mole of baking soda. And then for every 1 mole of baking soda, I would do the molar mass of the baking soda, and that would get me my mass of baking soda needed to neutralize that much acid. Yes? Make sense? All right, next up. It says that we have 2 drops of concentrated ammonia. About 91 liters are added to 10 mils of hydrochloric acid. What is the final pH? Right, ding, ding, ding. I know the amounts of 2 reactants, and this is just like problem 111 from the textbook. So, oh, this should say 91 microliters. Okay, are added to 10 mils of my solution. So ammonia, this part's important, right, is a base. That is a base you should memorize. You should know that one, and I do expect you to know that. So we'll have our HCl plus my NH3. Now, if this is a base, what kind of base is it? Right, it's got to be a Bronsted-Lowry base because it doesn't have hydroxide in it, which means it's a proton acceptor, right? So if we think about what that means, right, it's got to accept a proton from here, right? Which means that is what we produce, right? And if you want to write it like this, or you could just as well say NH4Cl aqueous, and that would be fine, and either one is absolutely fine, and I don't care. So if we check, it is balanced 1-to-1 ratio, and so now we just need to figure out which is limiting and which is excess. So if I have 91 microliters, let's go and start there, right? So 91 microliters, right, of my NH3. I know that for every 10 to the 6th microliters, I have 1 liter. And I know that for every 14.8 moles, I have 1 liter of NH3. And then let's go ahead and go to a product. So for a 1 mole of NH3, let's say 1 mole of NH4+. And that's going to be the work we need to do to come up with how much NH4+ we can make from there. So we'd have 91. All right, doing the second piece of work, we could have 0.1 liters of moles per liter of HCl, and for every 1 mole of HCl, we produce 1 mole of NH4+. So 0.0092 moles of NH4+. All right, so which of these is limiting? Right, this is my limiting, which means that this is my excess, right? Well, this is my excess. So just like we did in class, we need to figure out how much is left over. So we're going to start from my limiting, right, which is my 91 microliters of NH3. I'm going to convert that to normal liters, and then I'm going to figure out how many moles I have. And then I'm going to figure out how much of the other one I use, right? So for every 1 mole of NH3, I would consume 1 mole of HCl. So if I look at those numbers, I would get 0.001347 moles of, and let's label this well, consumed. Where I know that I start with 0.0092 moles of HCl begin. Yes, does that make sense? As in, this piece of math here gives me my moles of HCl I started with, which is this, right? And this difference here is going to give us how much we use. Or how much is left over, sorry. Moles of HCl remain. And so then just like in class, now all we got to do is we have to take this, turn it into a molarity. So let's go ahead and do that. So let's go ahead and take this and turn it into a molarity. How do we do that? Right, we're going to divide it by volume. So our total volume is going to be 10 mils plus 91 microliters. And then if we think about where microliters are, it's so many decimal places removed that it's irrelevant. So we have divided by 10 liters. That many liters. So then we get and then now what? Right. Then we're going to go ahead and take the negative log of this because this is also the concentration of that because it would dissociate. So we'd go ahead and do the negative log of my answer, and that's going to give us our final pH. Which is then equal to, yes, good. So literally the exact same concept as number 111 from your textbook. If you finished all the review packet problems and you feel like you need some more practice, don't forget that in your book there are all those even problems that correspond to the odd ones. And I do have answers for those in my room. So you're welcome to do those and come check them and see how it's going. All right. Thank you for listening. Be good. Practice, practice, and I'll see you soon. Bye.